After solving case in the fluent, the next part is the CFD post, and make sure the solution cell should be having this green tick mark. If not, then you can right click here and click on update. And now we're going to open the CFD post by double clicking on the result cell here. And this will open the CFD post. Now let me show you something here, that what things we should be doing here. Number one is that for this part we have to define the new coordinate frame, because in CFD post we don't have the luxury of having the built-in functions for the drag and the lift coefficient like we do in the fluent. So here we have to create that thing by ourselves. So, and also we don't have any angle of attack concept in the CFD post or in the CFX even. So from the user locations and plots, you have to insert and click on the coordinate frame. So I will be putting the name, short name here. So coordinate 1. Here I'm going to put this coordinate on the 0, 0 location, because the lift and drag, they are determined on this location. But the momentum is determined on the center of its momentum, which is usually speaking is the 30%. And but for this arrow file, the maximum camber is at the 40%, so maybe 0.4. But for lift and drag, we just use the 0, 0, 0. And in this xy, this point, we have to just put the value. This is 1 is for the 0 angle. This is the cost component, this side component. So I am going to use the same value as we did for these angles. But this time this will be done for the coordinate frame system here. And again I am going to use the y. For the y, I am going to use the sine component of the 4 degrees. Paste value here and then click on the apply. You can see this is a new frame is set here. And you can change the size of this new coordinate system by putting the value of symbol size as the 0.1. And just to give an example, if you just put the value as a 1 for the sine and 0 for the cos, which is 90 degrees, you can see this is over here. So x is upward and the y is on the other side. So anyhow, we have to revert back to the same values we need for the 4 degrees angle of attack. And this is the sine component, this is the cos component, which should be in the x-axis, and apply. Okay, next thing is to define these expressions. So I'm going to define these expressions. So just write down these values in this way. And the names can be different. So from expressions, right click here and click on the new. So for density, put the name density and click on OK. Density we are going to use is the 1.225 and space, then start the square bracket, and units are kilogram per meter cube. So kilogram will be written in the small letters, then the meter, because this is the power -3, it comes on the upside, so the power will be the -3 here, and then close the square bracket, apply. And if you don't see any error message, then we are all right. Again, I'm going to use the reference area. So REF area. The reference area would be equal to 1 because the coordinate is 1, depth is 1. And only thing we define is the units, which are meter square. The third thing is the incoming velocity or the free stream velocity. So V inlet or V infinite, that is the V of the free stream velocity. And dead velocity, you should be putting the exact value of dead velocity. And that's equal to 43.822 meter per second. So I'll just copy this from this PPT file. You can also type from the keyboard and paste here. So 43.822, again square bracket, meter. So M for meter, then space. Second, for the second we put the S and then power -1 and bracket close. And for the lift coefficient would be along the y-axis and drag coefficient will be along the x-axis. And these are the expressions for the lift and the drag coefficients. So you have to just, the force x is the built-in function in the CFD post, so you have to just use it, but just add the new coordinate frame, because we this in this picture, this name was the coordinate frame 1, but here we change the name to the coordinate 1, so put that name and then just put this expression. So just let me show you the same expression here, new and the drag coefficient. Name can be anything, but should not be the name of the existing variable in the CFD post. So this name can be any name which is not the part of database of the CFD post. So first of all, I'm going to use the function CFD post, and the force x, this is for the drag coefficient. For lift coefficient, this will be the force y. And the addition I'm going to make is the coordinate 1, C-O-O-R-D. C is a capital, C-O-O-R-D 1. So C-O-O-R-D 1. Where it should be on the aerofoil. So location is the aerofoil. And before we go for the drag coefficient, I just want to confirm that the expression is correct or not. So yes, correct. There is no error because we have added the new thing, which is not a part of the predefined command in the CFD post, which is the coordinate 1. And then I divide by the numerator, the denominator of the CL and the CD, which is the same for the both expressions. And here I'm going to put the value 0.5 times density. So right click here and put the expression of the density times the reference area. So again the expression, this is the reference area, and then we start the bracket for the velocity square. So again expression is the velocity infinite, which is the free stream velocity, power 2 for the square, and bracket close and overall bracket close, and click on apply. Okay, just copy this expression, edit and copy, and I will create a new expression for the lift coefficient. So I will just copy this syntax for the new expression here, and I will just modify the x to the y. That's all for the lift coefficient. And then now click on the table, and from the table you can write down let's say this is the drag coefficient, and this is the lift coefficient. We're just putting the headings for, so that we don't get confused if you open this file after maybe few times. And here we are going to put the expression that is for the drag coefficient. Click on enter key. You can change the size of text from here. You can change how the data is displayed, the number format, so you can put it fixed, and the precision means the number of decimal places 4. So 0.0316. If I put the one more space, I can be comparing the data with the Fluent. That was the 0.1361. Because the same results are there, so the results should be same in the CFD post or in the Fluent post processing. And for lift coefficient, I'm going to again right click here in the expression, choose the lift coefficient, and press the enter key from keyboard. Again the same thing will be done here, same settings, and the value is 0.83248. You can also check it from here, which is the 0.832. So same values we have because we didn't write down the more decimal places for lift coefficient. So this is now end of this whole workshop. You can see that for the different geometry, how to make the geometry in the domain the design molder, and then we follow the same procedure like we did for NACA 0012, and then finally we use the CFD post to make the lift and drag coefficient expressions. And before that we made the expression for density, reference area, and the velocity. But the benefit here is that if you change anything in the geometry, in the meshing or in the fluent part, like you can change the Reynolds number by changing the velocity, density, or viscosity, or you can change the angle of attack. So these expressions will be same. But just for the angle of attack, you have to put that angle of attack coordinates for the x cos alpha for the x here and sine alpha here. So for 10 degrees angle of attack, only this thing will be changed. Otherwise, all expression will be saved inside here. You have to just solve the case, just open the CFD post, you will get the results saved here in this format. Definitely this will be the different results for the different angle of attack or the Reynolds number, a different mesh, but this will save you time.